So thank you everybody for coming to this TCS Plus talk on this decodability of structured random codes by Mary Wootters. Mary Wootters is currently at CMU at Carnegie Mellon and is interested in applied probabilities and coding theory, and apparently on brontosauruses, as far as I can tell, given a PhD thesis. So yeah, there is.
I did not expect anyone to read that far.
So before starting, let's just go around the table to see who was there. So we've got a group from Berkeley, a group from IITH. I'm kind of bad at pronunciation, so yeah, I'm just gonna go around. So
Yeah, I can take over. For me, it's easier to see.
Okay.
Yeah, it's easier for me to see the list. Also, I should welcome Clément for helping us, joining us and helping with the operation. So we have Grant Schoenberg from the Michigan group. Hi, Grant. We have Japang with the UCSD group. Hi, guys. Welcome. We have Jo Briet from the NYU group. Hi, guys. Alina Fontes from the Paris group. Hi, everyone. Oh, it's dark. It's already dark there. And there's Muthu Ramakrishnan from Rochester. Hello. Hi, everyone. Piyush, and also Tomai there from Caltech. Suresh is joining us from Utah, and that's all for now. I think we might have another group joining later on. So, okay, that's it. Back to you, Clément.
Oh, yeah, so this talk is on list decodability of structured random codes. It's so Mary Wootters from CMU, and it's joint work with Atri Rudra. So yeah, if you're ready to start. Oh, yeah. Before, so the next talks that are scheduled on the 22nd, there's going to be a talk on satisfiability and evolution by Christos Papadimitriou, and we're going to send an announcement. And again, the schedule as well as past talks and abstracts, all that can be found on the official site of the TCS Plus seminar series.
Okay. Can I start now? Good. All right. Well, thanks, Clément, very much for the introduction, and thanks for the organizers for inviting me, and thanks for everyone else for tuning in on the internets. Yeah, so I'm going to talk about the list decodability of structured random codes, and this is joint work with Atri Rudra. And I also want to say, I know this format isn't super conducive to asking questions, but please do your best to interrupt me and unmute yourselves whenever if anything is unclear. Okay, so this talk is mostly about, well, it's about list decodability, so let me start out by setting up the problem and defining a couple of the main things that we'll be studying. First, let's just talk about list decoding. So in the coding theory problem, Alice wants to talk to Bob over a noisy channel. So this channel, there's some bad guy who lives in it, and the bad guy is going to corrupt some of the message that Alice wants to send to Bob. So let's say that Alice, has some tactical message she wants to send to Bob. So maybe she says, "Attack at dawn," and she knows that someone is going to mess this up. And so what do Alice and Bob do? Well, they want to introduce some redundancy in their message. So maybe Alice will say something like this, say her message several times, or use a lot of synonyms, or something like that, so that, even if some enemy were to corrupt a certain fraction of her message, Bob can still basically know what to do. So I guess here the sword is for attacking, and the bagel is for breakfast, because dawn. Anyway, okay. So that's the the storybook version. To be slightly more precise, how are Alice and Bob going to achieve this? They're going to employ something called an error correcting code. And so for me, an error correcting code is just a subset of fq to the n. So here's my picture of fq to the n, this big green blob here. And the code is just the set of all of these red dots. So each one of these dots represents a vector of length n, and each entry in this vector is a symbol from fq, the finite field of size q, okay, which is called the alphabet for the code. And we imagine this code has good distance, that is relative Hamming distance, let's say delta. So that means that for any two code words here, any two of these red dots, they differ from each other in at least a delta fraction of the symbols. So why do we care about such objects? Well, because Alice and Bob can use them for communication. Right, so here's Alice and there's Bob, and beforehand they agree, maybe via some encoding map, how to assign messages to each of these code words. So for example, like this. And so maybe Alice wants to say attack at dawn, so she wants to send Bob this code word here in the middle. Oh, you can even see my mouse. Great. Cool. So she wants to send Bob this code word here in the middle. And now it's where the distance of the code comes in. So let's say she takes that code word, so it's a list of n symbols over fq, and she sends it to Bob. And now this bad guy who lives in the channel, he's going to corrupt some constant fraction of them, say maybe a row fraction of them. And what Bob is going to see, whoops, there we go, is this corrupted code word w, which is just a little bit different than what Alice meant to say. And the point is that if the bad guy corrupted only a row fraction and row is less than delta over 2, then Bob can tell uniquely which code word Alice meant to send. And then he can just sort of round back and prepare accordingly. So that's the basic idea. And in coding theory, we sort of care about the trade-off between two things. First, we would like to maximize the number of errors that Alice and Bob can tolerate. So that's this row, which is called the error rate of the code. So there we go. So the error rate is row. And the other thing that they want to maximize is the rate, or the information rate of the code, which measures the amount of redundancy that Alice has to use when sending things. So how many Q-array symbols could she send? How much information theoretically is she sending? She's sending log base Q of the size of the code symbols. So log base Q of the number of messages she could possibly send. And how many symbols does she end up sending? She ends up sending n of them. And so the rate is defined to be this ratio, the ratio of the number of symbols she wanted to send divided by the number of symbols she actually ended up sending. So this is a number that's always between 0 and 1, and Alice and Bob would like to make it as close to 1 as possible, while keeping this tolerable error rate row rather large. So there's a basic limitation here, which you can see from my little cartoon, is that if this error rate row is quite large, let's say bigger than a half, or in general bigger than half the distance of the code, then there's nothing Alice and Bob can do. Right? So it's possible that the situation would look like this, that this point here goes very far away from all of the red dots, and Bob doesn't know what to do. And if the error rate is bigger than a half, or bigger than delta over 2, there's really no way around this. So instead of throwing up our hands and saying they can't communicate, we'll make the best of a bad situation and introduce and redefine the problem. And so we're going to introduce something called list decoding. And the basic idea here is that Bob doesn't know maybe exactly what Alice meant to send, but it's not like he doesn't have any information. He knows maybe that she meant to send one of these blue code words, something close to W. And so formally, we would say that the code is list decodable if for any code word W like this that Bob might see, there's not too many other code words that lie close to it. So here's a definition. We say that a code is row L list decodable if for any center W, the number of code words that lie in a ball of radius rho around that center is no more than L. And this parameter, capital L here, is called the list size. So in my cartoon here, this picture here on the left is sort of nicely list decodable. It's row 4 list decodable, because wherever I plop down that point W, there's no more than 4 code words that are going to live in that ball. Whereas the picture on the right is not very well list decodable. If there is some point W that I can plop down that contains a lot of red code words. So that's the definition. And it turns out this turns out to be pretty good for Alice and Bob. So it turns out, and I'm actually going to prove this later because it's not hard to see, that there exist codes which are row L list decodable, which can correct almost 100% of errors. That is, if this error rate rho is like 1 minus epsilon, so almost every single symbol is corrupted, Alice and Bob can still do something non-trivial, which I think is pretty cool. And so these parameters that I've listed here are sort of the parameter regime that I'm going to talk about for the talk. So let's just sort of take a minute to internalize them. So it turns out you can get codes with this ginormous error rate, 1 minus epsilon, with positive information rate on the order of epsilon. So it's small, but it's still positive. They can say something. And with list sizes that are reasonable, where here reasonable means something like 1 over epsilon. Right. So in particular, none of these numbers depend on n. So if epsilon is a very small constant, all of these numbers are constant. So this is great. This makes Alice and Bob very happy because they can win this game with non-trivial list sizes, pretty short list sizes, even if nearly 100% of the message is corrupted. So that's great. It turns out it's good not just for Alice and Bob. List decodable codes have applications sort of throughout complexity theory and pseudo-randomness. Just as a combinatorial object, a bunch of points that don't all lie in too many balls is a useful thing to have around, and there's lots of connections which have been very well studied to things like extractors and expanders and all your sort of favorite pseudo-random gadgets. So I'd recommend, I guess, either of these excellent surveys for more on that. Okay. So that's a brief introduction to list decoding. This talk is mostly about the list decodability of Reed-Solomon codes. So let me tell you next a little bit about Reed-Solomon codes. Okay, so here's the definition of a Reed-Solomon code. So a code, remember, was just a subset of fq to the n. And another way I could say is it's a map that takes messages and spits out code words. And so for Reed-Solomon codes, the message is like this. So Alice has some message she wants to send, which is actually a polynomial over fq of degree less than k. So you can think of this as a k symbols over fq, which are the coefficients of this polynomial that she would like to send to Bob. And how does she encode this? She just evaluates this polynomial at n points, alpha 1 through alpha n. And these points are called the evaluation points that live in fq. So it's often standard to take these evaluation points, this set alpha 1 through alpha n, to be the entire field fq. For me, it's actually going to be important that we can choose them as we like. So we have freedom to choose our evaluation points as we want. Okay. And so Reed-Solomon codes have been around for a very long time. They're very well studied. In particular, here's two useful things about them. They have good distance and good rate. So particularly the rate is k over n. Right? Alice wants to send k symbols, the k coefficients of her polynomial, and she ends up sending n symbols, her n evaluation points, so k divided by n. And the distance is basically 1 minus the rate. And that just follows because any two polynomials of degree at most k minus 1 can agree in at most k minus 1 points. So these are codes that they're very great. Right? So they've been around for a long time, used all over the place. They are used in QR codes and CDs and in the Voyager spacecraft, lots of places. Okay, so that's Reed-Solomon codes. What do we know about the list decodability of Reed-Solomon codes? So one thing we know just sort of follows from the distance of the codes. So there's this thing called the Johnson bound, which basically says that any code with good distance has good list decodability. And intuitively, this makes sense, right? If we have that picture where I had all those red dots, if those red dots are all pretty spread apart pairwise, then it makes sense that not too many of them can live in a ball of radius rho. And you can prove some statement to that effect. It's called the Johnson bound. And what you get when you plug in those distance parameters, and that for Reed-Solomon codes that we saw earlier, is that if you take a Reed-Solomon code of rate about epsilon squared, for any epsilon greater than 0, then this can be list decodable with polynomial size list sizes up to error rate 1 minus epsilon. Okay, so that's great. That still hits this 1 minus epsilon error rate that we were after, which is pretty cool. And actually, one of the really cool things about Reed-Solomon codes, and one of the reasons why they are so important in the list decoding literature, is that you can actually achieve this algorithmically. So the celebrated Guruswamy-Sudan algorithm is an algorithm that actually lets you find this list of code words. It lets Bob find this list of code words efficiently with this parameter regime.
We've got a question from Suresh. Is the fact that the error rate is 1 minus the distance something which is more true for the error correcting codes, or at least desirable?
Sorry, say again?
Is the fact that the error rate is roughly 1 minus the distance some fact which is morally true for ECCs, or?
So that's called the singleton bound. So that's the best you can do. Right. So that is a morally true fact, in that's a natural limitation, and so Reed-Solomon codes meet that. So yes, it's not always true. I can find a code with terrible rate and terrible distance if I so choose, but that is a limit. Does that answer your question?
Yes.
Yeah. Okay. Cool. Yeah. Great question. Yeah. All right, so that's one of the reasons that Reed-Solomon codes are so great, is because they do sort of achieve this optimal trade-off between rate and distance. Okay, right. Yeah, so they achieve this great trade-off, and you can plug that into the Johnson bound, and you get this other trade-off between rate and the error rate up to which you can list decode. But unfortunately, this one is not so optimal, right? Because remember, I said before that there are some codes of rate epsilon that can handle this error rate, and for list decoding, this is the limit here. This is optimal, and that's also a morally true fact, and not hard to see. I guess just sort of in a hand-wavy information theoretic sense, if you are corrupting 1 minus epsilon fraction of the information, there's only an epsilon fraction of the information left to send. You can make that rigorous, and it's called the list decoding capacity theorem. And so there's a gap here. Sort of what we would be after optimally is something like rate epsilon, and what we get from the Johnson bound is something like rate epsilon squared. And one of the main questions after this work was, well, can you close this gap? So I said before that it's not hard to see that you can close this gap. Actually, a random code gets this optimal trade-off, and I'll prove that in a few slides. But the main question is, well, can we get a nice code? Can we get something like Reed-Solomon code, something structured, something with an efficient decoding algorithm that closes this gap? So that's a great question. It was well studied, and now we know the answer, which is yes. Right. So there's this first result about Reed-Solomon codes. It was followed by a result of Parvaresh and Vardy, which sort of beat this epsilon squared barrier, and then finally, the work of Guruswamy and Rudra introduced something called folded Reed-Solomon codes, which are a variant on Reed-Solomon codes, which should have actually closed this gap and answered the question. And since then, there's been many other constructions of nice codes, mostly related to Reed-Solomon codes, but not exactly Reed-Solomon codes, which attain this optimal trade-off. And so the starting point for this work is that, so there's all these codes which have this optimal trade-off that are all kind of similar to Reed-Solomon codes, but none of them are Reed-Solomon codes themselves. And so the motivating question is, are there Reed-Solomon codes, that is, can I pick evaluation points, which are list decodable beyond the Johnson bound? Can I beat this epsilon squared for Reed-Solomon codes themselves? And here I should note that even a combinatorial result is interesting and was unknown, even if I don't ask for an efficient decoding algorithm. So this is, yeah, even this was unknown.
So, Mary?
Mm-hmm.
Just in the last slide, you mentioned that there is a result achieve that. But I guess subcodes mean a number of arbitrary subspace, not just evaluation points, right?
Right. So subcodes mean not choosing the evaluation points, but then also choosing particular polynomials.
Okay, I see. Thanks.
Yeah. Right. Any more questions? Okay. So let me motivate this question a little bit. So I guess it was first asked by the work of Guruswamy in Sudan in the late 90s. And why is it interesting? Well, I think it's interesting for several reasons. So first, Reed-Solomon codes are very well studied, and it's good to understand the combinatorial properties of these well-studied codes. Another point I want to make is that if you're not maybe too familiar with the list decoding literature or with its connections to pseudorandomness, you might say, well, rate epsilon squared, these are all really small positive numbers. What's the big difference? It turns out that this distinction actually does matter for some of the applications to complexity theory. So this is sort of the important parameter regime for those applications. And finally, more of a philosophical question is what is with this epsilon squared barrier? So this barrier it comes up a lot, the Johnson bound. It's a very natural barrier, and understanding what's necessary to get beyond it is an interesting complex question. Oops. I'm getting some feedback. Oh, okay, good. Cool. Okay, so like I said before, this is a well-studied question. Lots of people have looked at it, and there's been some conflicting evidence both ways. So there's some reasons to think that the answer might be yes. So these reasons are, for example, that Reed-Solomon codes are really nice. They're optimal in a lot of other ways. They're our favorite codes ever. Surely they must be great here too, right? Another reason is that all those other constructions we saw are variants of, or many of those other constructions are variants of Reed-Solomon codes, like either appropriate subcodes or foldings of Reed-Solomon codes or so on. However, there's also some evidence in the negative direction. So for example, it's known that if you were to take all of the evaluation points, so alpha 1 through alpha n is equal to the entire field, or even more generally, if it contains certain algebraic structures, then the answer is no. You can't push the rate much beyond epsilon squared. And this is a result of Ben-Sasson, Kaparti, and Radhakrishnan. Another reason maybe to think the answer is no is that there's an analogous statement to the Johnson bound for something called list recovery, which is kind of a similar problem to list decoding. And for those analogous settings, it turns out the Johnson bound is the right answer for Reed-Solomon codes. So it's goes both ways. And so the point of this talk now, 20 minutes in, I can actually state the punchline, is that the answer is actually yes. And in fact, most Reed-Solomon codes are list decodable beyond the Johnson bound. They can beat this epsilon squared barrier. And by most, I mean that if you take random evaluation points with very high probability, this is going to work. And in fact, the techniques that we use are more general and apply to lots of structured ensembles of random codes, hence the title of the talk. And so we also get some corollaries for random linear codes and more generally randomly punctured codes, which I'll talk about in a little bit. Okay, so that's sort of the end of the background material. Are there any more questions before I go on to results?
One quick question. You could, you might want, maybe you're going to say it later anyway, but construction, do you know how to choose those?
No, I do not. And yeah, so that I will state that later as an open question at the end. Okay. That's a very good question.
Or,
yeah, I don't know.
I mean, can you verify if a set of, give
also
us
a
points?
very good question. Yeah.
Okay.
We don't have anything like that, and I think that's a very good question.
Good. Okay. Thanks.
Okay. Any other questions? Okay, so just to get something concrete here on the screen, let me state the result for Reed-Solomon codes, and then I'm going to back up and zoom out about 10 billion feet and state a much more general result. And then basically I'm going to spend the rest of the talk stating this more general result, which is moderately technical. So I'll start out really zoomed out and then hopefully zoom back in a manageable way. But first, just for closure and concreteness, here's the result for Reed-Solomon codes. And so it says that if Q is big enough, and here for Reed-Solomon codes, we generally think of Q, the size of the field, as being huge. This is an innocuous statement. And if you choose random evaluation points, like I said, and so how many of them do you choose? Choose them so that K, the degree of the polynomials divided by N, is like this. So the rate is like epsilon divided by some log chunk. And so recall that the right answer for this rate was like epsilon. We were hoping to get something bigger than epsilon squared. So this isn't the right answer because of the log chunk, but it is, for certain parameter regimes, bigger than epsilon squared and closer to epsilon. So that's the result, which is nearly optimal after these log factors. And so then the conclusion is that with high probability, the corresponding Reed-Solomon code is list decodable in this very high error parameter regime. So it can, even if this bad guy corrupts a 1 minus rho fraction of the errors, Alice and Bob can still win with reasonable list sizes. All right, so that's the result for Reed-Solomon codes. Now I'm going to step back and state a very hand-wavy result of which this is a corollary. So here's the hand-wavy result, and it's hand-wavy enough that I had to put 2 sets of quotations around the word theorem. And so the result is that any code with enough randomness that smells about right is nearly optimally list decodable. Okay, so now I have to do 2 things, which is to tell you what enough randomness is and also what it means for a random code to smell about right. All right, and so I'm basically going to spend most of the rest of the talk answering those 2 questions. Okay, so in order to maybe motivate motivate that statement and also motivate what smelling right means and what enough randomness means, let's prove an easy result, which is that if I take a completely random code, then this is as list decodable as I like. So, or list decodable up to capacity. So that is to say, by completely random code, I mean I start out with fq to the n, and I just start putting down random dots. There they go. All these random dots. And the result, which is the classical result, is that if the rate is less than epsilon, then this random code with high probability is list decodable up to error rate 1 minus epsilon, with list sizes about 1 over epsilon. Okay, so here's the proof of that statement. Very simple. So what do we want to show? We want to show that for any center W, there are not too many code words that lie in a ball around W. All right, so let's pick the center W. So there it is, this green dot. I just realized that, in fact, pointing at the screen doesn't actually help the audience see anything. I'll use my mouse. Yeah, so start with this green dot W. Here's a ball of radius 1 minus epsilon around W. We want to show that it's unlikely that lots of the code words land in this. Okay, well, so what's the probability that a single code word lands in this ball? It turns out it's not very large, right? It could land anywhere in fq to the n. The probability that it lands in this ball is not very big. It turns out it's something like q to the negative epsilon n when q is very large. Okay, so it's some tiny, tiny number. And then now I want to do this for lots of points, right? I've only failed the list decodability check if L plus 1 points land in this ball. So let's fix L plus 1 messages. What's the probability that L plus 1 of these encodings land in this ball? It's even smaller, right? Because all the code words are independent, if the probability of one of these events is small, then the probability that L plus 1 of them happen is like small to the L minus 1. So that's just an astronomically small number, very small. And in particular, it's small enough that we can take a union bound now over all possible centers and all possible sets of these L plus 1 points. So if let's do that, we union bound over q to the n possible points W and over q to the k choose L plus 1 possible sets lambda. We multiply that times our very small failure probability. We wave our hands and do some approximations, and this is something like this number here, q to the n plus k times L minus n times epsilon times L. And if you stare at that, you can see that if you pick L to be on the order of 1 over epsilon, and you pick the rate, which is k over n, to be on the order of epsilon, then this failure probability, the probability that there exists any bad event, is very small. So if that means that if I take the parameters that I claimed on the previous slide, so L about 1 over epsilon and R about epsilon, then with high probability this code is row epsilon list decodable. Okay. All right, so that's great. So let's try this for Reed-Solomon codes now. Let's see what goes wrong. Okay, so we can do the same argument. Let's fix a possible received word in FQ to the n. We'll look at this ball of radius rho around this received word. What's the probability that one code word lands in this ball? Well, it's still quite small. Same value of small. All right. Now a code word, remember, is a bunch of evaluation points of a polynomial. There's a polynomial evaluated on endpoints. It's very unlikely it lands in this ball. Okay, so but now comes the catch. Now we pick a whole bunch of these polynomials, right? And in particular, now these things aren't independent anymore, right? They have the same evaluation points. They might be, very related to each other. And so I can't do this small to the L plus 1 trick anymore. The best I can do, I guess, is say that the probability that all these guys lie in the ball, without any fancier stuff, is just as small as it was that one of them might lie in the ball, let's say. And so that's still a small number, but it's not small enough to allow us to take the union bound. So if you try, you'll get nothing. Right, so that it just doesn't work because there's not an independence here.
Just one thing to make sure.
Mm-hmm.
The randomness now is over the choice of the evaluation points, right?
That's right. Yeah. So the randomness is over the choice of this alpha 1 through alpha n. So in particular, each one of these code words themselves, all of the symbols of them are independent from each other, but between these two code words, they're not independent.
I see. Okay, thanks.
Okay, yeah, and so actually I'm going to make that maybe even more clear in just a minute. All right, so this proof doesn't work for Reed-Solomon codes. That's a bummer. But let's look on the bright side. We do have a few things going for us. So one thing going for us is that before we took the union bound, things weren't entirely hopeless. So that by that I mean here, the probability that this bad event happened was small. It's not small enough, but it's pretty small. So we'll say before the union bound, things aren't hopeless. The other thing we have going for us is, right, we don't have that the code words are independent from each other anymore. But like Oded was just asking, we do have that within a code word, the symbols are independent. Right? So here the randomness is over the choice of these evaluation points, alpha 1 through alpha n. So here's my cartoon of 4 code words. So here's a code word corresponding to F. Here's a code word corresponding to G. Here's a code word corresponding to some polynomial P, and so on. Right? And so these code words now are not independent from each other, but if I were to just look at this one code word, F, all of these symbols are independent. So we do have some randomness to work with. And so now I'm going to restate that theorem that I had before, but now instead of with 2 levels of quotation, of air quotes around it, I've only got 1 level of air quotes.
There's some noise on your... can you just say it again, because there was lots of noise in the background.
Where I am?
Oh, yeah. I think it's coming from somewhere in your computer. And it's only me that hears that.
I mean, I
don't hear.
Maybe you can try disconnecting your headset and just using the internal microphone.
Oh, okay.
You can use it to ask the question. Yeah. You have to disconnect the headset so we hear it. You can try to hear the internal microphone. Try to connect again, see if we can hear you.
No.
No, there's no voice whatsoever. We can hear you. We can do it. Yeah, we can just read from the slides. Can you try to connect again the headset? Because we can see you, we can see the slides, but we don't hear any audio now. Okay. Well, we can use the opportunity and mention the next few talks.
Okay. Maybe try to see on your Google Hangout thing. There is that in the settings. Maybe you can select the new audio source since you switched it.
Okay, that sounds right. Yeah. Google Hangout settings is at the top. You should be able to choose the microphone. That must be it. Yeah, things always happen, right? Either we have fire power shutdowns. Yeah.
Does that work?
Okay, you're back.
Yeah.
Cool.
And I think we've got a question from Suresh too.
So we're good?
Yeah, we can hear you. Suresh, do you want to ask a question?
Oh.
Even though he does use it.
The controversial difficulties.
Oh, so the question is, how do you choose the polynomials f, g, p, and q?
So in the code we include all polynomials. How I chose the names f, g, p, and q is that I listed f and then g, and then I had to think of some more polynomial sounding names. But yeah, in the code, all of the polynomials of degree up to k-1.
Okay, and there is one particular per message, so the message defines the polynomial.
That's right. So the message is the polynomial, basically. So Alice's message space is all lists of k things in FQ, and she's going to interpret that message, that list of k things in FQ, as a polynomial, as coefficients of a polynomial. And then she'll send her message by just evaluating this polynomial at the points alpha 1 through alpha n. And those are the things that are random that we get to choose. Does that answer the question?
Apparently, yes.
Okay.
But n is bigger than k, right? And these things are not really independent, right?
N is bigger than k. That's true.
Then all these evaluations are not really independent, right?
They are. So n is bigger than k. Q is bigger than n.
Oh, okay.
Right.
Q is bigger than okay.
Size must be at least n for a Reed-Solomon code. And for us, Q might be yeah.
Okay, I'm just confused about. So f is not random, right? F is like fixed, right?
F is fixed, yeah. So imagine instead of writing 4 possible code words here, I had written q to the k possible code words here. That's how many there are. All of the polynomials. I just can't draw q to the k things on a slide.
Mm-hmm. If my polynomial is just say the constant 1 polynomial, then how come f of alpha 1, f of alpha 2 up to f of alpha n, how can it be independent?
I see. Right, that's true. Okay, so maybe let's. Okay, they're independent random variables, but they're degenerate, right? They're independent over the choice of alpha 1 through alpha n. So in that case, it would be like I'm taking a bunch of independent draws from the constant distribution. I guess, if you want to be. Oh, now I can't hear you.
Hi.
Sorry, that's my fault. Yeah, I understand. So you're saying they might not be, they don't have to be uniform, but they're all taken from the same distribution.
That's right. Yeah. So they're all. I choose these alpha i's independently with replacement from FQ.
Okay. So, but apart from that annoying constant case, they're really just independent and uniform. Yeah.
So are we allowing repetition of alphas?
Yes, we are. If you want, you can redo all of the results not allowing for that, but the computations are slightly easier with the full independence. So let's just say we'll take them independently with replacement.
Okay.
If you want not replacement, the same results are also true. And follows from an easy argument. Just on paper. Any more questions? That's a good one. Okay, so now we understand this distribution. Let me state sort of my second level of theorem here, which says that if those two things hold, so that is, if things aren't hopeless before the union bound, and if you sort of have this independence symbol-wise, so this would apply to Reed-Solomon codes with random evaluation points like we just discussed, but also to, you know, let's say random linear codes or many other ensembles of codes, then you get this conclusion that we are after, that C is list decodable with error rate 1 minus epsilon and list size about 1 over epsilon. And so here are these two conditions. This first one, not being hopeless before the union bound, corresponds to the condition that I was calling smelling right beforehand. And this independence within the symbols is the enough randomness condition. Okay. Okay, so now I want to remove this final level of quotations and actually state the theorem. So in order to state this theorem, I need to define one more concept called average radius list decodability. So here it is defined in a picture. So average radius list decodability is like list decodability, but a little bit stronger. So let's recall the definition of list decodability. That's this picture here on the left. So what list decodability means is that if I have any set of L+1 code words, so L+1 red dots, then at least one of them lies further from this center point W than rho. So at least one of those L+1 things lies outside this ball. You could say that the maximum distance of all of these L+1 things from their center is bigger than rho. So average radius list decodability is that same thing, except I replace the word maximum with the word average. So if I have any set, that's this picture here on the right, if I have any set of L+1 code words, then the average distance from their center should be bigger than rho. All right. And this is a stronger notion because the average is always less than the maximum. So if the average distance is bigger, then certainly the maximum distance is bigger. So average radius list decodability implies list decodability. So actually, we're going to prove average radius list decodability. And it's slightly easier to work with because it kind of linearizes the problem, which we'll see in a minute. Okay, so I was trying to avoid writing down too many symbols, but it's going to be useful later just to see one string of symbols. So here it comes. So here's that average radius list decodability picture that I just had. Here's a definition in symbols. So this is exactly the definition that we just had. If you take the max over all sets lambda of size L+1, so the worst possible set lambda, and you take the max over all possible received words that Bob might see, Z, so the worst possible center, then, so like as I said, their average agreements should be, or their average distance should be big. That's the same as saying their average agreement should be small. So let's write that. So the sum of all of the agreement between this center and the encoding of this X should be not too big. And it turns out this value on the right here is the correct number of not too big. Okay. So this is just symbolization of the picture. It's nothing fancy. But just remember, this is the thing in the purple box that means average radius less decoding. All right. So now I think with that out of the way, I can state the theorem that implies this Reed-Solomon result that I said before. Okay, so I'm not going to state it quite yet. I'll state it with some placeholders first, and then I fill in the placeholders one at a time. So the general result goes something like this. So suppose that C is a random code with independent symbols, so that's the enough randomness condition, so that something else holds for all sets of size L plus 1. Something's going to go in this yellow box, which is going to correspond to the smells right condition, which is going to be something related to average radiusless decodability. And I'll get to that in a minute. And the rate of R is not too big. And so here, the rate, I'll fill this in more precisely in a moment. I just don't want to put too many symbols on all at once. The rate is going to be what we had before when Q is big, so something like C epsilon squared divided by log, or sorry, C times epsilon divided by log stuff. If Q is very big, so far for Reed-Solomon codes, Q is always very big. And so that's all I've been talking about, but actually our result holds for small alphabet sizes as well, and we get something about right, and the correct answer in that parameter regime is slightly different, and we get something close to the correct answer there as well. And I'll fill that in a minute. So then if this rate is about right, and you have these other two conditions, enough randomness and smelling correct, which I'll define more rigorously in a second, then the conclusion is that this code is average radiusless decodable up to this very large error rate. So before I was saying 1 minus epsilon because I was assuming Q was gimungous. If Q is not gimungous, then 1 minus 1 over Q minus epsilon is the natural sort of large enough radius you can hope for. And list size is L, I should say L is like 1 over polynomial n epsilon with high probability. So that's the statement. Or that's not quite the statement. So here's the statement. So now I've
quick question, sorry, can you say again what you mean by a random code with independent symbols for a general code? I got it for Reed-Solomon, but in general?
Right, so in general I mean that the symbols are independent. So
what are
the ith position, if I look at all of the positions of this code, that they're independent random variables. So if you want, you can imagine that I'm going to write down. I'm going to write down my code as like a big matrix where all of the columns are code words, and I'm picking the rows of this matrix independently at random from some distribution.
So maybe another way of saying it is that you think of the code as a mapping from some domain into this FQN. You're saying that for each element in the domain, its image, if you consider its distribution over the choice of this random code, has IID symbols. Is that precise?
I think so. Yeah, so let me say again. I think I'll just say what you just said. Maybe. So let's think of a code as a mapping. So I'm going to think of it as a function that spits out n numbers. So I'm going to think about it as n functions, f1 dot fn, and each of them take in a message and spit out a symbol in fq, and I get my code word by concatenating all of these things. And what I'm saying that each of those functions, f1 through fn, those are all chosen independently from each other from some distribution. Yeah, so actually the identically is not seen, but they're independent.
Thanks.
Okay. All right. Yeah, so that's what the independent symbols means. And you can look at the paper if you want sort of precise definitions with lots of notation.
But that's a very mild constraint. You could easily get that by just multiplying each symbol by a random number, and that shouldn't be enough to get this decodability.
Right, but you would need to have this smelling right constraint as well, which in that case might not hold. But yeah, you're right. So that is a reasonably mild condition. It does hold for yeah, right. any sort of polynomial evaluation code where you pick the evaluation points independently. It holds for random linear codes. I'll give a couple of more examples later.
Okay, thanks. No, we can only do voice and audio. We cannot do smell yet. So.
Right. So I will try to make that more rigorous in just a second. Yeah. So let me, before I talk about the smelling right condition, which is this thing in the yellow box, let me talk about the rate condition, which is just kind of ugly. So this is the rate we actually get. So it's the better of these two things. There's two different arguments. For very large Q, this reduces to the statement that I showed earlier for Reed-Solomon codes, and for medium-sized Q, it's a little bit more complicated. I just want to throw up briefly what the correct answer is. So the best rate you could possibly get as Q and epsilon varies is 1 minus the Q area entropy of 1 minus 1 over Q minus epsilon, which is sort of written out what you get if you just sort of take a first-order Taylor approximation, or if you take a Taylor approximation to these guys here. So for very big Q, you would hope for something like epsilon, and for more medium-sized Q, you'd hope for something like this, Q epsilon squared divided by log Q. And so we have elements of all of that here. So here you get the Q epsilon squared over log Q for medium-sized Q, or the epsilon for large Q, but then there's some extra log factors which don't belong there. And for a constant Q, we get the correct dependence on epsilon. Okay, so that's the rate. It's nearly optimal with the exception of some log junk. Okay, and now finally I need to explain what this thing in the yellow box is. Okay, so here's this condition. And I just want to compare it to that definition of average radiusless decodability that I had before. So remember, average radiusless decodability said that if I look at the worst possible set lambda, I look at the worst possible center, the average agreement between that set lambda and its center should not be very big. Okay. And let's just say we want this to hold an expectation. All right, so the thing in the purple box is the thing we would like to establish. The thing in the yellow box is the thing that we're assuming. And how do they differ from each other? Just actually in these first two symbols. So this is the condition that we want to show is to bound the expectation of the maximum of a bunch of stuff. And the assumption in the theorem is that the maximum of the expectation of a bunch of stuff is not too big. Right? And so that's what I mean by is reasonably well behaved before you take the union bound. So I can, if it's okay before I take the union bound, before I take this maximum over all of those sets lambda outside, then it's okay afterwards. And so this is good for applying the theorem because it's much easier to bound the maximum of the expectation of stuff than it is to bound the expectation of the maximum of stuff. Yeah. Okay, so that's the smelling right condition. And so that's what the theorem says, is that if you have enough randomness, that's this independent symbol stuff, and if everything is okay before you take the union bound, meaning that you can switch the expectation of the maximum in the definition of average radiusless decodability and everything's fine, then as long as the rate is nearly what it's supposed to be, you get this list decodability result. Okay. And so let me just say some examples where this holds. So one is where C is a random linear code, so that is just take it to be a random subspace of FQ to the n. Another example is this Reed-Solomon codes with random evaluation points. Another example is a random puncturing of any code with good distance. Turns out satisfies this. So by that I mean, here's a code. My code words are columns here. And by puncturing I mean, let's take a random subset of the symbols, or maybe I can, with or without replacement, doesn't actually matter, but for the independence, let's say I take them with replacement, take some symbols with replacement, throw out the rest. Now what I've got is a code with better rate, and it turns out it satisfies this smells right condition. And actually the first two points here are a special case of this one. A random linear code is a random puncturing of the Hadamard code. A Reed-Solomon code of random evaluation points is a puncturing of the Reed-Solomon code with all of the evaluation points. So this is slightly more general. There are some other things that fit into this framework, like if I sort of take I'm going to call this a random folding, even though it's not quite right. So I take a code word, a code with, say, constant distance, and I just sort of start, I create a new code over a bigger alphabet by taking random symbols of my previous code word and just lumping them together. that it turns out also satisfies this condition. So this is pretty general. And so the punchline is then that for all of these things, for these weirdo constructions or these sort of generic transformations, as well as for specific families of codes like random linear codes or Reed-Solomon codes, you get optimal list decodability or near optimal list decodability out in the end. Okay, so I guess I took a little bit longer than I intended. So in the next 5 minutes or so, let me sort of briefly sketch some of the ideas that go into the proof. Okay, so remember that we want to establish this average radius list decodability condition. So for all sets of size L plus 1, on average, they're pretty far from their center. So the average agreement between everything in this set and the worst case is not too big. And the basic observation is that with a little, pushing symbols around, we can write this as a sum of independent things. So what is this quantity we want to control? So here's my cartoon of a code here. So it's all my code words are written as columns here, and I guess here the alphabet has size 4. The alphabet is red, green, blue, and yellow. And I'm interested in some set, lambda, of code words. So this is L plus 1 code words. And I want to study the average distance of this set from its center. Okay, so here's its center from the worst possible W. So it's actually not too hard to see what the worst possible W is. I can just sort of go coordinate by coordinate. So here, here's this set. For this particular set, what is the worst possible W that Bob could see? Well, so here in the first position, I should put, whichever color shows up most frequently here. So let's just put a yellow. In this next position, I should put whichever color shows up most frequently here. So green, and so on. Okay, so this is the W which maximally agrees with this set. And I can write down how much it agrees. So this yellow agrees in 2 places with this first row, and this green agrees in 5 places with this next row, and so on. And then the thing that we want to control, this average agreement of lambda with the worst possible W, so that's this random variable that we'd like to control, is just it's the sum of these numbers. Right? So 2 plus 5 plus 2 plus 3 plus 3 plus 2 in this case. And I can write that as the sum of what I'm going to call the pluralities, which is because you can call this the plurality because this is how many times the most frequent symbol occurs in each row. And the point here is that because the symbols were chosen independently, these pluralities are independent. So this is a sum of n independent random variables. And what we want to do is say that this sum doesn't get too large over all of the possible lambdas. Okay. And so to show that C is list decodable, it suffices to show average radius list decodability, which means that this thing, the expectation of the maximum of this sum of independent random variables, is pretty small. So that's what we're going to do. And so recall we assumed that the maximum of the expectation was small. When we switched expectation to maximum, that was okay. That's the smelling right condition. And then what remains to be shown is that that was a legit thing to do. It's usually not allowed to switch expectations and maxima, so in order to make that legit, we should show something like this, that without switching the expectation and the maximum, the sum, sort of the worst case deviation of the sum of these pluralities from their expectation is also not too big. And then the triangle inequality will prove what we want. Okay. Okay, so that was the hypothesis, and we want to show this concentration thing. So I realize that it is now 2, so I should probably stop talking, but I maybe have 5 more slides of this. Should I stop and skip?
I think
on it, or
usually don't rush it. So if you stop, you could stop and then hear more details. It's up to you.
If screens down below start popping off, I won't be offended. So the rest of the time, I guess I'll take 5 more minutes and wave my hands at sort of how to prove this concentration bound, and I'll try not to rush. I think I should only need 5 more minutes or so, but I won't be offended if the internet wanders off. Okay. So the basic trade-off here is we want to show that this sum of independent random variables is small, and the bigger n is, the more concentration we have, the easier this is going to be to show. But the bigger n is, the worse the rate is, and so we want to pick the sort of the smallest n possible so that we can still show this. So maybe I'll skip this slide. So we already said that the union bound doesn't work, right? Because we don't have independence between code words, it turns out these plurality random variables are not very well concentrated. And so we've already tried to do this argument. If you try to do the union bound, it doesn't work. So instead, what we're going to do is a better union bound, right? So the main observation is that if lambda and lambda prime are close to each other, then a union bound is kind of wasteful. So what do I mean by that? So in this picture here, here's a set lambda, and here's a set lambda prime, and whatever close means, these guys are unambiguously pretty close to each other. They overlap a lot. And I look at this list of pluralities that I have here. Remember, we want to control the sum of these numbers. And the sum of these numbers for lambda and the sum of these numbers for lambda prime are very correlated, right? So here, the most common symbol in this top row for lambda is yellow, and there are 2 of them. And the most common symbol on this top row for lambda prime is also yellow, and there are 3 of them. I mean, so these numbers are close, and they don't differ by very much. And so on. So these are very correlated random variables. And so the point is that taking the union bound here is like saying that, okay, so now I know that lambda is well behaved, that the sum of the pluralities of lambda is well behaved. Now I'm going to throw up my hands and say I don't know anything about lambda prime. And that's not true. Conditioned on lambda being well behaved, I expect lambda prime to be pretty well behaved. I should have a very high probability there. And so we want to somehow take advantage of this correlation structure. And so there's a standard way to take advantage of relationships like this when you're looking at Gaussian processes. And so formally what we do is introduce some Gaussians and manipulate those. So here's how I introduce Gauss. But I'm going to not go into that to avoid getting too bogged down in details. But just morally, yeah, maybe I'll skip the next few slides and here. But basically, the idea is that we do a chaining argument, and so we create some nets on these sets of lambda, and actually construct these increments between lambda and lambda prime that are close, and sort of take a union bound in that way, in a more structured way. And the main insight is this thing here, that we need to take advantage of the fact that there's a lot of structure and a lot of correlation going on here. So let's skip that. So that's the basic high-level idea of the proof. So let me just briefly conclude. So what have I talked about? I talked about sort of a general method for establishing the list decodability of structured random codes. And some punchlines were that there are Reed-Solomon codes which are list decodable beyond the Johnson bound. Some other punchlines which I didn't go too much into detail about were that random linear codes are nearly optimally list decodable. So the list decodability of random linear codes has been studied for a while and is now reasonably well understood for small alphabet sizes and for small error rates. But so the advantage here is that this can handle both very large error rates and very large alphabet sizes. Gets the near optimal right answer. I mentioned this result about sort of randomly puncturing any code with good distance. You can get a nearly optimally list decodable code. So I guess you could say this is kind of like a randomized version of the Johnson bound or something, which is gets a slightly better result. Yeah. So those are a few punchlines. As many punchlines as there are plenty of questions. So one of the main open questions, or one of the most obvious open questions, is to remove all these log factors that we have. So that there was a bunch of log 1 over epsilon factors. There was also a log q factor there, which needed to be there in the small q regime, which didn't need to be there in the big q regime. And for Reed-Solomon codes in particular, it's kind of especially obnoxious because we think about q as being very, very large. So removing that would be great. And related as finding a simpler proof. So I didn't go too much into the details, but it gets a little gets a little bit hairy, and I feel like there should be a simpler way to take advantage of this correlation structure. One thing is the question that was asked earlier about actually finding a Reed-Solomon code or certifying that a Reed-Solomon code, certifying that a particular set of evaluation points is good. We've just shown that many of them exist. I have no idea how to actually find one efficiently. I think that's a very interesting open question. Another open question is, what else can you hit with this hammer? So I gave a couple of examples of structured ensembles of codes that smell right and have enough independence. Can you think of more? If you have a favorite structured ensemble of code and you want to know the list decodability of it and you think it might be interesting, I'd love to hear about it. Just a plug, there's a few more applications and some recent work with Autry you can find on my website. And finally, applications to other pseudorandom objects. So like I mentioned before, list decodability is very related to extractors and expanders and gadgets like that, and maybe could these sorts of techniques be used in those problems as well. Okay. So that's all. So thank you very much for listening, and sorry for the technical difficulties. Are there any more questions? All right. That's yeah.
So I have a question.
Yeah.
So you showed that, I mean, this concentration theorem, I guess, which you did not show in so much detail how you did this, but how should I say? You showed that essentially this, where you replace the union bound, right? Essentially, you have for every subset you have a random variable, like the sum of the pluralities, and you know that they are very correlated. So if the two subsets overlap a lot, then the random variables are very small, and that allows you to improve on the union bound. Is that right?
That's right.
So this seems like rather general or kind of a thing which should be interesting on its own. Is this like can this be made kind of a standalone theorem, or do you know any other applications of such a thing?
Yes, this is a very general thing, and especially when the random variables you're interested in happen to be Gaussians, so when you're interested in a Gaussian process, which is what we end up reducing to, then this sort of thing is very well understood, and it turns out that the supremum, the expected supremum of a Gaussian process indexed by some set is basically completely captured by the geometry of the set. So what we end up doing is what's called a chaining argument, which we didn't come up with. It's very general and standard, and I guess the reference might be Talleyrand's book, The Generic Chaining. And in fact, you can show, and this is called the majorizing measures theorem, that for any such process, there is a chaining argument that can prove that, or that will give you the right answer for the supremum of it. So the answer is yes, this is very general, and these tools are very general, and we did not come up with them, and they're well studied. So I can talk more with you about it offline if you want, or give you some pointers.
I've got another question, which is more related to one of the open questions. So you mentioned, for example, the log Q you'd like to shave off, but where do you think that comes from? Does that come from like at that swapping expectation maximum, or is it more like more intrinsic to the approach itself at some other place?
Yes, that's a really good question. So the log Q, it does need to be there for small q. So the right answer is given by this Q area entropy, and if you sort of write out what the Q area entropy looks like for small q, it kind of the correct dependence on q is something like q divided by log q, and for very large q compared to epsilon, the correct dependence on q is none whatsoever. And so yeah, so I've thought a lot about that question, and I don't have a satisfying answer that would allow that log Q to be there when it needs to be there, and not in this other parameter regime when it doesn't need to be there. So maybe, yeah. So I think I can add your question to my list of open questions that I would like answered as
Okay.
where exactly
What
is that necessary? Yeah, I think that's a very good question. But I'm afraid I don't have a satisfying answer to that.
Is there any connection to that recent work on the covering time of graphs, where I believe the chaining was also used, and recently it was shown how to do it in a deterministic way? Is there any connection, or?
I mean, so there is connection in that. I guess the buzzwords are the same, right? Like it's both. So I'm not super familiar with that work, but it's right. They use the majorizing measures theorem, right, of the generic chain like that.
But I guess the way they de-randomized is not something that obviously applies here. I guess that's what I meant to ask.
Oh, okay. So I hesitate to say no because I haven't thought about it very much. But that's a good question. I should take a look and see if that could help de-randomizing something here. I'm not sure.
I'm also curious. I'm curious about the technical part. Namely, I should think of L as being rather small, right? L is constant, right?
L, yeah, you should think of L as being. So I think of L as being like 1 over epsilon, and think about epsilon as being a very small constant.
Right. Because we have tons of subsets of size L. And most of them don't intersect. It's actually very unusual for two to intersect. So I think of them as being essentially disjoint. So I find surprising you can gain so much above unit bound because they're essentially disjoint, all the subsets.
That's true.
Does that make sense?
Yeah. Yeah. So let's see. So here's a way to. So I had those two results on the rate. Oh no, that's the wrong way. There we go. And then the statement of this theorem, where'd it go? There it goes. There's this two results for the rate. And so if you look at the second result here, which has completely the incorrect dependence on Q, but the correct dependence on epsilon. So this actually comes from an earlier paper about list decoding random linear codes. Over small alphabets, and the argument there is similar but a lot easier. And so for that argument, so I'm going to return to your question. For that argument, so basically the idea is this: let's think about all these sets of size L as, I don't know, vectors, 0, 1 vectors of L1 norm L. And if I look at the supremum of whatever this thing is that I want to look at over all of those vectors, turns out you can write it as like a linear thing, and this is no bigger than if I replace all vectors, all 0, 1 vectors with L1s in them with all vectors in the L1 ball of radius L, let's say. Right. So you're asking how is it that this complicated thing where most of these sets don't overlap could have relationships with each other? But if I think about, instead of thinking about this as the set of sets of size L, instead I think about it as vectors in the L1 ball. Now all of a sudden, if I'm interested in the supremum of some Gaussian process, let's say over indexed by the L1 ball, all I really care about is the corners of this ball, right?
Right, and there are very few of them, just the size of the code right, the number of code words, that's all, right? Not to the power L.
Right, exactly. So it's n of them rather than n to the L of them. And so maybe that's one way, morally, to answer your question. And you can actually make that argument rigorous, just replacing these sets with this L1 ball, and you get this result here, which it doesn't have the right dependence on Q, but maybe it's a little more intuition to it. Right. So the relationship is that even though they don't intersect a lot, they all have something to do with, at the root there are only sort of n coordinates which are contributing to any of them, and if you can control those, then you can control everything.
So n, you mean the capital, the Q to the Q, Q to the K.
Size of the code. Sorry. Yeah. Sorry. They're only size of C.
Okay. Yeah, because there's another in here.
Does that kind of answer your question a little bit?
Yeah, I think it's clear. So basically, all these random variables are actually subset sums of the individual code words. So that's
Yeah, and that's actually how this chaining argument that we do here goes. So let me show you some of the slides that I skipped. Right. So the basic idea is we don't actually. So this was my lying picture of what's going on, is that this lambda is close to this lambda prime. That what we actually do is we look at subsets. So we say that the thing that's actually correlated is, so if here's some set lambda, and I look at a subset of size lambda over 2, then the fraction of guys that are yellow in this top row is very similar to the fraction of guys that are yellow in this top row, and those are the things that are correlated. And then we sort of do this chaining argument down until we get down to sets of size 1. And then you have to sort of take the union bound over those, of which there are not very many. There are size of C of them instead of size of C for all of them.
okay. Thanks.
Any other questions?
Okay, so there are no questions. Let me just thank again all those who join us, and I'll just mention again, we might have Christos Papadimitriou next time in 2 weeks. Anything else, Clément, that I forgot?
I don't think so, at least no. Otherwise, I forgot as well. But...
Okay, thanks. Okay, so I go, let me turn off the live broadcast, but those of you that are still here are welcome to stay. We can have some informal discussions now. So let me just stop the broadcast. Okay, thanks.